All right, it's 2:03. I think we can get started. So, hello everyone, welcome to Ask Seminar Series. I'm John, the seminar coordinator, and I will be moderating this seminar with Kathy, our communication specialist. Also joining us is our director, Ralph Ferrero, and Ralph will be introducing the speaker. This seminar is being recorded and we will publish the recording on our YouTube channel. The Q&A session will be and after the presentation, so you are welcome to bring up any questions you have. We encourage you to speak out, or if you don't have a mic, you can chat us your questions and we will read it out. Let me hand this over to our director, Ralph Ferrero. Ralph, please go ahead.
Yes, yeah. So we welcome our speaker, Tracey Holloway from University of Wisconsin. She's got a joint appointment at Institute for Environmental Studies and also Atmospheric and Oceanic Sciences. She does a lot of air quality policy type work. Let's see, she serves on NASA Health and Air Quality Science Team, and she's won some awards with the AGU and MIT. And let's see, she's got her PhD from Atmospheric Oceanic Sciences at Princeton. I also saw she got undergraduate degree applied math from Brown, and she also did a postdoc at Columbia University at the School of Public Health. So turn it back to Tracey and look forward to her talk.
Well, thank you so much, Ralph and John, and to the organizers. It's a real pleasure to be here today. The only thing that would make it better is if we were actually here today together. But it's nice that we can connect virtually through this seminar series. So I'm going to be talking today about some of the work that we've been doing around air quality, as well as some bigger picture issues related to making science and data relevant to different constituencies. And, I think of this broadly as decision making because, often people talk about science and policy, but I would say policy is just one type of decision making, which goes from regulatory decision making to new laws. But there's also decision making at the household level for community groups, for nonprofits, and more, and businesses. So, I think that oftentimes the mechanisms that work to bridge user needs with one group are common across other groups. And air quality is unique in that it connects with so many different parts of our economy. We all breathe the air. And there's a lot of expensive and powerful laws here in the US, as well as connections with climate and energy and health around the world. So to get started, I want to first give a shout out to the different folks in my group whose work I'll be talking about today. Science is a team sport, and my group really works together collaboratively, including some of the senior scientists in my group, Monica Harkey, Paul Meyer, Jenny Bradbert, recent PhDs, including Alicia Hoffman and Gesayanji, some current graduate students, Drashti Amin and Cici Orth, and some recent grads who have gone on to other things, including Jennifer McGinnis at Colorado State and Colleen Heck at the consulting company ERM. And much of our work is funded by NASA, as well as the EPA and nonprofit organizations, including the McKnight Foundation and the Center for Applied Environmental Law and Policy. So when we think about air quality, we're really talking about chemicals in the air that impact public health and affect visibility, affect ecosystems, acid deposition, and some of these also affect climate. But most of my work deals with the United States, and most of it deals with pollutants that are regulated under the Clean Air Act. And for these types of pollutants, there are three main sources of data. There are measurements taken in situ, mostly at ground-based monitors, especially at the gold standard monitors managed by states and tribes in compliance with EPA standards. There are also advanced computer models, and my group runs a number of these models, which I'll be talking about later. And evolving over the past decade or so, which I'll also be talking about, is the potential for satellite data to support air quality decision-making. So when we're thinking about the data of air quality, it usually comes from one of these three sources: monitors, models, or satellites. But none of this data would be connected with the real problems of air quality, of course, without the scientists. And thanks to this group photo from our Utah meeting of the NASA HICAS team last fall. So there's the science of air quality, but there are also so many other stakeholders who have a vested interest in air quality on a day-to-day basis and who rely on the science coming from these same data sources and the insights from the scientific community. And just to sort of use these figures as a shout out, so I don't forget to mention some of the big organizations, it includes regulated industries, the transportation sector and urban planning. It includes governments from the local to the national. It includes major nonprofits like the Sierra Club logo. It includes the regulatory agencies. And here's the logo for the National Association of Clean Air Agencies. It includes community groups who are advocating for clean air in their own community. It includes all humans because we're all breathing air, and kids are an especially vulnerable group. And it also ties into the growing for-profit sectors interested in clean air issues, whether those be Google supporting the air quality alerts on your phone, or consulting companies, or low-cost monitors, or other kind of startup companies working in this space. There are others too, but I say this because often as scientists, we think that, we're focused on, of course, ourselves and our data and problems, but these are operating in the context of this wider ecosystem. And, just as one example of how air quality managers can use some of this data, there's this cycle that is sometimes, described as setting goals. And the goals through the Clean Air Act are called the National Ambient Air Quality Standards, that are thresholds. Once you have a threshold, then the question is, well, how much do we have to change our emissions to meet that threshold? How are we going to develop those strategies? How do we want to implement those reductions? And then how can we tell if these reductions are working? And really, scientific research from all of these different data sources and more can affect this management cycle. And that's just one of many decision frameworks that relate to air quality. So when thinking about how to get science into these frameworks, it really depends on which framework you're talking about and which type of data. But one that I've been especially connected with over the past 10 years has been trying to connect satellite data into these decision frameworks, because I lead the NASA Health and Air Quality Applied Sciences team, which I'll tell you about in a few minutes. But this is really NASA's effort to build a bridge between billions of dollars of satellite data for atmospheric composition and almost anyone who could possibly use it, from international organizations to community groups, nonprofits, to state regulators, and more. And sorry for my energy efficient lights, which I'll have to turn back on periodically. So here I'm showing a really nice study that came out at the end of last year that was focused on the UK, but I think many of the insights pertain to the US as well. And these researchers, led by graduate student Dan Potts, separated respondents into two categories. One that we might call scientists, researchers, and the other one that we could consider data users or stakeholders. And these might be consultants or government regulators or public health professionals. And I'll be referring to some of the results from this really nice study through the course of my talk today. So one of the questions that they asked these two groups is, have you ever collaborated with the other group on the incorporation of satellite data into air quality management activities? And the answer is no. Neither group, 80% of neither group had collaborated with the other in thinking about how satellite data could be useful. But would you be interested in a knowledge exchange program where satellite data experts and end users work collaboratively to utilize satellite air quality data? And remember, this is in the UK. And I will say that one of the examples of this knowledge exchange program that they gave was the NASA Team I Lead. And we'll come to that in a few minutes. But would these hypothetical users be interested in this kind of exchange program? And the answer was a resounding yes, that about 90% would like to have more connection. And I think that this idea that both scientists and practitioners are not working together, but want to be working together, bears relevance to many of our work here in the US, and thinking about why, what are the barriers to be impeding this collaborative work. And drawing on this UK study, they found that the scientists were interested in difficulties around funding and lack of time. The stakeholders had a more wide-ranging source of reasons of why they weren't engaging with satellite data or collaborating yet. One was a lack of communication, a lack of understanding of different groups' needs, and maybe not seeing a clear benefit to a collaboration. So this really tees up why NASA has been funding the Health and Air Quality Applied Sciences team, now going on 8 years. And there's a new solicitation that came out about 2 or 3 weeks ago through Roses, and they'll be recompeting this team in the coming year. So the mission of this NASA team is really to bring the power of NASA science down to earth and deliver it into your hands. That there's billions of dollars of taxpayer-funded resources, and how can we maximize the societal benefit of those data? Now, when we're talking about satellite data, really this is referring to the entire constellation of Earth-observing satellites, some of which are observing swaths of the Earth every day or every few days. And the newest addition to this constellation of satellite data products is the TEMPO instrument, which was launched last year. And test data have been released to the scientific community, but there's no public data released yet because there's still quality controlling TEMPO. That is expected to be released to the public on May 6th. So this is certainly a big, an exciting advancement, because TEMPO is the first satellite that will provide hourly data on gas phase air pollutants over the United States. And it's one of 3 instruments planned on a global basis, one called GEMS that was launched over South Korea, and looking at Asia was launched a couple of years ago, and TEMPO over the United States. And then there's a partner satellite planned over Europe as well. So we have these data. They see many of the constituents that are of concern for public health and air quality management. And so if you think, do scientists think that these are useful to potential end users, and do the end users think that they're useful? And so if we look at this research, and indeed here's where we get a much bigger spread. The scientists and researchers think that in their current state, at least about 90% of respondents felt that satellite data were useful, but over 50% of respondents did not think the data were useful. And herein lies the challenge that we're trying to tackle with HACAST, is trying to understand, what does useful mean to potential end user organizations, and where are we seeing success, and where might be the next success around the corner. So HACAST is the Health and Applied Air Quality Applied Sciences team. It's a 4-year initiative that's running through 2025 in its current generation, which has 14 members. and 60 co-investigators with the mission of connecting NASA science with air quality and health applications. Our initiative has 4 main types of work. There are the projects that the 14 members or PIs proposed in their NASA Roses proposals. There are collaborative projects that we call Tiger Teams that formed over the course of the HACAST projects. There's rapid response projects that are intended to address emergent needs that are even more rapid than the one-year Tiger Teams. And then we also do a lot of outreach and engagement to connect with new organizations and to build partnerships with across our team, but also in the wider community. So this 3rd generation of HACAST builds on a success that NASA has been funding since 2011. And the first generation of this effort was called ACAST, the Air Quality Applied Sciences Team. And that effort had 19 PIs and focused really on US air quality. And Russ Dickerson, who was just on the call a few minutes ago, he was on ACAST, and it was really a pleasure to get to know him and the great work going on in Maryland through that initiative. In 2016, it was recompeted as HACAST, which had a health and air quality focus, including the US and global communities. That ran through 2020, and then it was recompeted in 2024 to run through 2025. And so that's where we are now. And across these 3 generations of this initiative, we've learned a lot. And we've learned that really having a team structure fundamentally changes the outcomes rather than having a collection of PIs individually funded, even if they were funded with the same mandate to go forth and have partnerships and collaborations. We found that having a team increases the visibility of work and resources to end users to sort of operate like a front door, so that organizations who are interested in satellite applications don't have to be Googling lots of different scientists. They can have one point of connection and a cohesive interface. We built a culture across our team to promote collaborations, to grow 2-way dialogues where we're listening to organizations as well as sharing cool science and data products. Increasing collaborations to meet stakeholder needs, because oftentimes the research program of any one group or PI may not fit the exact needs of an organization. But if that organization wants research on a topic, probably you could put together a dream team of collaborators to address their needs. So this idea that rather than trying to match the problem to what I'm already doing, how can we work together to truly address the needs of our partners? And then when we see something that's working with one organization or through one collaboration, how can we replicate that and spin it up as quickly as possible? So the team of our current generation of HACAST has these 14 PIs. They represent universities and government research labs spanning Alaska to Florida, including Brian Duncan at Goddard there in Maryland, and really a wide scope. And beyond these PIs, each one of us is working with a network of co-investigators as well as students and postdocs and partner collaborators. So I'm happy to talk during the Q&A about what participation in HACAST looks like, especially if anyone here is thinking about applying to the current solicitation. And you can see more at our website, which is hacast.org. One of the ways that we build cohesion across the team and connect with stakeholder partners outside of the team is by having in-person hybrid meetings every 6 months. So we had a meeting in Utah in October. We're meeting in Massachusetts in June. And through these meetings, we do our best to bring the scientists and the external partners together. We have panels that are usually 50-50 kind of scientist stakeholder. We have poster sessions. We have a lot of time for Q&A and networking, and really with this goal of trying to engineer collaborations across different groups that might not normally work together. Just as one example of the kind of work that I've been doing personally with my HACAST hat on, has been to think about how satellite data estimates of PM 2.5 could be used by new organizations. And one organization that I've been working closely with has been the American Lung Association, which issues grades to US counties every year. And in fact, they just came out earlier this week with their 2024 State of the Air report. And the State of the Air report issues A through F grades for daily ozone and daily PM 2.5, and they issue passing and failing grades for annual average PM 2.5. But in all of these cases, currently they calculate the grades based on ground monitoring data from the EPA network. But only about a third of US counties have even a single monitor. So this is really missing a lot of the story of what PM 2.5 looks like across the US. So one of the tasks that I got started early in our project was to work with my former student, Colleen Heck, and review every publicly available satellite-derived PM 2.5 data set that existed, compare them with each other, and think about different ways of analyzing the data to be comparable to the monitor-based grade from the American Lung Association. And just to get a little bit into the what we did is that what the ALA does to calculate their grades is they look across a county and assign the grade based on the highest monitor in the county. And so we looked at a few different ways of analyzing the data, but found the most consistent results when we looked at all the different grid boxes in a county and calculated a grade based on the highest grid box in a county in a more analogous way, which I would not have thought of except having meetings with our partners and hearing their perspectives of what would make sense. And so here we have a map of every county in the continental United States, ranked from dirtiest, that's number 1, to cleanest, that's number 3,143. And we see patterns across the US that are not evident when we look at just monitoring data because we're missing so many monitors. So this is just one example of how a problem from a stakeholder organization has driven our analysis and led us to new ways of thinking about data analysis, new results. This paper is on my to-do list to submit to a journal. And in fact, the American Lung Association is coming out with a report this summer that we're also contributing to on how satellite data might be useful in their own outreach and engagement work. So that's just one example of my own work as in the blue line here, this idea that we have over the course of this 4-year grant. Each of us proposed activities that we would do with partners to get selected to be on the team, and those are ongoing. Then we also had in 2021 a competition for Tiger Team ideas that were these collaborations across the team. And then we had a second round of Tiger Teams competed in 2023. And now, as we are in spring of 2024, we are moving into the last year of this grant. And with this, our meeting at MIT in June, and then we'll be having a showcase meeting probably in January 2025 at NASA headquarters in DC. And then, of course, we have the recompetition for the 4th generation of this activity that's we're all probably thinking about proposals for now. So these Tiger Teams that were selected in 2023, just to give you kind of an idea of what these look like. One is led by Arlene Fiore, looking at how tempo can best be applied to surface ozone in support of air quality and health information needs. One led by my colleague here at Wisconsin, Brad Pierce, looking at how to improve lateral boundary conditions for regional air quality modeling. One led by Ted Russell at Georgia Tech on thinking about how satellite observations can better evaluate exposures from oil and gas extraction emissions. One led by Shen Zhao at the Texas Medical Center, thinking about how satellite data can support environmental justice. And this is the only Tiger team that's now in its second generation. Usually the Tiger teams are kind of one and done, 1-year projects. But the first Tiger team, which also was led by Shen and Susan Annenberg at George Washington University, was really considered such a success that not only has there been a second Tiger team, but in fact, NASA has launched a new initiative under their Earth Action Program, specifically on equity and environmental justice. And that's had now 2 funding cycles. And sometimes our program manager has described this Tiger team activity under HACAST as kind of the pathfinder for environmental justice activities at NASA more broadly. And then the third initiative of the 2023 Tiger teams is using GOES-R aerosol data to support public health decision-making. And that's led by Yang Liu at Emory University. So this kind of gives you an idea of the scope of the work and the kind of the projects that have bubbled up as being highest priorities to our stakeholders. These were selected not just by having stakeholder partners, but actually the reviewers who ranked them were all from different private and public sector organizations that our team has been working with. We have developed a website that is intended to be this front door, and it has not just tools and resources, but also ways to get started, resources for educators, a glossary, because there are so many terminology acronyms, level 3 data or AOD, that can be a real barrier to organizations that want to start using satellite data but haven't done that. And so we've really designed our website to try to lower the barriers for new organizations getting involved and ramp up the value of these data to organizations that already find it helpful. We've launched a community forum at haq.community.forum. It's not quite as active as we would like, but we've been hearing for years that stakeholders want a help desk for resources. And NASA already has the Earth data platform for Q&A, but that tends to be very technical. And we wanted to have a place that people could ask even basic getting started questions and connect with like-minded users. We have also launched the HACAST Ambassadors Initiative. We realized that there's some organizations that were consistently coming to our meetings and contributing to reports, and we kind of informally called them the super users. And we wanted to have a way to bring these super users together and have more direct back and forth so that they could be advising on some of our decision points and that we could be learning from their insights. And so these are the groups of our ambassadors currently. And just as an example of how some of this work is helping our team, at our meeting in Massachusetts in June, actually for the very first time, we're having a pre-meeting hosted by the Health Effects Institute and focused really on early career researchers and what do they need to learn to build effective partnerships between atmospheric research and health research. And I don't think that early career pre-meeting would have come about if we hadn't had 2 members of the Health Effects Institute engaged as our ambassadors. And, you know, one of the ideas that came from this ambassadors meeting has been ideas to try to, you know, make those train tracks or pathways that can connect what people actually want to know to where the data are as smooth and reasonable as possible. And so actually they had asked, could we make just a flow chart? And when they first asked me if they could make a flow chart, I was envisioning, you know, maybe one big page, maybe a legal sized page of arrows and charts to get from a problem to a solution. But Jennifer McGinnis, who led this effort in collaboration with me and Jenny Bradbert, found that the more you start pulling on this thread of what are all the possible starting points and what are all the possible ending points, It ended up becoming a 24-page clickable document. And so there's a lot of different ways that a path could go for users to navigate the ecosystem of data. But we've gotten a lot of positive feedback from stakeholder partners who found this this document, this website really useful, and so we're moving it into newer formats to be more adaptable and to grow as the landscape of data options grows. So I mentioned this meeting in Massachusetts. It is public. Anyone can come in person. Anyone can log on. So you're very much invited. And some of the lessons that we've learned from these activities is really that two-way dialogue is essential. We need to be listening to our partners just as much as we're telling them what we're doing. And that most organizations are busy and resource limited. So if you are wanting to build a collaboration, it's best to really start small with your expectations and their expectations so that you can get some early wins and build from there. Recognizing that relationships and trust grow over time. So the more that you can be doing to get to know each other and listen and learn each other's terminology, the better. Many organizations have political and organizational limits that may not apply to us as scientists. So it's good to be sensitive to those and just to build skill sets to engage with partners that may be different than the skill sets that are needed to make a cool graph. One book that I like was written by my friend Andy Hoffman. It's called The Engaged Scholar. It's very, very short, but it has a lot of nice insights into what it means to be doing research that is engaged with partners and issues beyond academia. So kind of moving to the data and moving to some of the issues, I wanted to kind of zoom in on a thread of work that we've been working on that I think kind of highlights our approach to linking data with decision making, and here around ozone. And here, this is a map of ozone design values from the EPA, and these are the values that are used to determine whether areas are passing or failing these threshold-based rules under the Clean Act, known as the National Ambient Air Quality Standards, or NAAQS. And so quite a few areas have failing monitors for ozone, but one of the challenges is that ozone is not directly emitted, but rather forms in the atmosphere through a reaction between NOx and VOCs. So we have these two ingredients that form ozone, and the question is, which of these makes more sense to regulate? Should we focus our money and policies and efforts on NOx, or should we focus it on VOCs? And the answer is really, it depends. It depends on the chemical environment that is creating the ozone and really the ratio of NOx to VOCs. And just as one way of thinking about this ratio, this is a satellite-based estimate of developed work by Xiaomeng Jin, who's now at Rutgers, Arlene Fiore at MIT, and others, where TROPOMI, no, this was for OMI data, sorry, the ozone monitoring instrument that was launched in 2004, and using this data to look at the NO2 from satellite and its ratio to formaldehyde from satellite. So the formaldehyde to NO2 ratio is used as a lens to estimate where areas may benefit from NOx controls, and that would be the NOx limited regime, the yellow, or where they may benefit instead from VOC controls, which would be the red, NOx saturated. And I think it's helpful to where does this come from? It kind of comes from this classic idea of this ozone isopleth diagram, where the shape of these curves is going to vary day to day and place to place. So this is really just a idealized way of thinking about this, but that for any level of ozone, you could have more VOCs and less NOx, or more NOx and less VOCs, or somewhere in the middle. And in general, areas that are urban areas are historically more likely to be VOC limited, and anywhere that's not an urban area is historically more likely to be NOx limited. But without measurements of NOx or measurements of VOCs, it's very hard to navigate where on this plot you might be and where how the decision to control NOx or VOCs could be informed by relevant data. So the idea that there are NOx to VOC ratios that can serve to inform ozone control policies was first advanced in the late 90s and early 2000s, especially work by Sandy Silman. And that was applied to satellite data in 2004 in a paper by Randall Martin and colleagues, using some earlier satellites to look at the ozone sensitivity to these precursors. And I'm going to step through this little timeline quickly, kind of as a case study of how the needs of users can cycle back and inform the scientific process, and how scientific advances can in turn be made more relevant to users. The work of Randall and colleagues was advanced to use the OMI satellite by Brian Duncan and colleagues in 2010. And shortly thereafter was when the ACAST team started, this first generation of this NASA initiative. And we met every 6 months back then too. And often we would have air quality managers attending our meetings. And, you know, I like to make small talk with new people. And my way of making small talk with new air quality managers would say, do you use satellite data in your work? Which back then in the 2012 era, the answer was almost always no. I don't use it. It's not relevant. I want the surface. They give me the column. But one time we had a meeting here in Madison, Wisconsin in 2012, and I asked this question of a Colorado air quality manager named Pat Reddy, and he said, yes, I love using satellite data. I especially love using OMI to evaluate the formaldehyde to nitrogen ratios following Brian Duncan's work. And I thought, wow, that's amazing. Like, here was a real air quality manager who had siphoned through the academic literature, found the paper he needed, and figured out how to download the data and make it work for him. And I was so excited about his story that I worked with a student of mine, Sarah Whitman, and worked with Pat himself, of course, to talk about his experience and write it up in 2014 for issue of the EM magazine, which is the magazine of the Air and Waste Management Association. So that got me excited about using formaldehyde to nitrogen ratios. And so when I had a master's student working with me named Xiaoming Jin, who we were thinking about what could be a policy relevant, energy relevant question to motivate her master's thesis here at the University of Wisconsin. And so she applied this same approach, looking at ozone sensitivity over China, and that was published in JGR in 2015. And so then when she went on to work with Arlene at Columbia, Arlene Fiore at Columbia, she continued this work through her PhD. And that was some of the work that I just showed you that was featured in the image of the day from NASA. So actually through Xiaoming's work, she's continued to refine how can we think about these thresholds? What does it mean to be NOx or VOC limited? And mainly looking at average quantities. But then analyzing work from the Long Island field campaign, looking at summertime ozone, Arlene and Xiaoming and another former student of mine who's now working with Arlene's group, Madame Kui Tao, started looking at high ozone days and low ozone days, and how might these ratios change on high ozone days and low ozone days. Now, over this time period, now we're caught up to 2022, air quality managers have consistently asked me, how can I replicate this study? How can I analyze formaldehyde data and nitrogen dioxide data from satellites to determine this ozone ratio? And so I had an intern working with me, Jennifer McGinnis, and I said to Jennifer, surely there must be some way that we could point users to replicate these really cool results. And so Jennifer went on a hunt where she was looking at all the kind of public-facing portals for satellite data analysis. And did they have, were they easy to use? Did they allow time averaging? Because the formaldehyde data is too noisy to be looking at day by day, and even the NO2 data is pretty noisy. So we need to be able to average over multiple days. We need to be able to divide the formaldehyde by the nitrogen to get that ratio. And we wanted to be able to use the highest resolution, newest global data from Tropomi. And so NASA Worldview is really the easiest platform, but it's limited in some of its abilities. NASA Giovanni gets us further. The Panoply platform gets us further. But really, we found that Google Earth Engine was this sweet spot where it wasn't quite as easy to use, but we didn't have to download any data, and there was a lot of documentation online. So Jennifer wrote up this for a special issue. It's not now accepted. It's been published last December, laying out an approach to use Google Earth Engine to evaluate ozone sensitivity. And this, we were able to replicate the results from Tao et al., both for New York City, and then we also did it for Denver, where we found that on higher ozone days, they tend to be more NOx limited. But because Jennifer was able to write up instructions in Google Earth Engine with a full tutorial, I love working with undergrads here at the University of Wisconsin-Madison, and having these tutorials that are meant for non-expert or not satellite data expert users is a perfect way for me to engage and on-ramp new undergrads in my group. So I asked one of my now she's been working with me for about a year, but at the time was new to my group, Ragad Bajuda, to follow Jennifer's tutorial using Google Earth Engine and replicate it for the 100 largest cities in the United States for all years. And so Ragad found that depending on the city, the results are a little more mixed. It's not always that hot days are more are more NOx limited. In Houston, it could be more NOx limited or more VOC limited. In Las Vegas, they tend to be more VOC limited as we get hotter days. And we're still digging into some of the causes and processes, but I think it's showing how basically we have this cycle where we hear what users want and we think about how to provide that. And in doing so, I think it's also advancing the educational mission that I'm working on here as a professor. If you're interested in using Google Earth Engine, you might think about, like going to our website, hollowaygroup.org. We have a special section on tutorials, and we have step-by-step instructions on how to use Google Earth Engine to calculate these ozone indicator ratios. But this has also made me think, is there a way to make Python easier too? Because there are things that we just can't do in Google Earth Engine, or we want to be empowering users to have full capabilities of downloading and analyzing whatever data they want to use. So this comes back to this nice survey from my colleagues in the UK, which also asked the question to scientists and data users of where would you rather download pre-processed uniform data sets or handle the original data? And I think this is really a culture difference between the scientific community and potential user groups, because most scientists want the raw data. They feel comfortable analyzing it. They have those Python or other data analysis skills. And this is quite different than most of the organizations that we're working with, who would rather have the data in a pre-processed format. And that might be Excel spreadsheets. It might mean GIS shapefiles. It might mean these web-based interfaces like Google, NASA Worldview. But I think if you're thinking about how to work with new partners, recognizing that the way that you use data as a scientist is probably different than the way a collaborator may want to use data for their own work. But in an effort to try to make these Python-based analysis methods more useful to organizations who want to take that step, two of my graduate students, Alicia Hoffman and Gesayanji, developed 8 user-friendly tutorials. And these are intended really for folks with no prior programming experience at all. Many of the undergrads coming into my group come from a wide range of different majors. I think I counted 14 at one point, and I don't want to force them to go take another class before they get looped into the fun of air quality research. So instead, we have these tutorials that really take students from the very beginning all the way up through analyzing net CDF and remote sensing. And about 6 months ago, I thought to myself, I wonder how many of my students have actually used these tutorials. So I asked our IT manager if he could send me the list of everybody who had downloaded these tutorials. And we were amazed to find that they've been used by hundreds and hundreds of users all around the world. So if you or your students want to get going using Python for air quality analysis or remote sensing, those are also available on our Holloway group /tutorials website. So I'm going to end this talk with a whirlwind discussion of models, because I love models. I was trained as an applied math major, and I really got into atmospheric science from a modeling perspective. And so I've been working with one of my graduate students, Drashti Amin, on thinking about how do these models relate to each other, and how do we find the best model for a problem? Because of course we each have our own favorite model, but that may or may not always be the right model for a policy relevant or decision relevant question. So first we were looking at the peer-reviewed papers in Web of Science, and looking both at papers by US authors and authors outside of the US. And we found that if you look at all papers that are published, CMAC is the most published paper, which is not surprising because you have to run it separately for one country or another country, or one region, another region. WRF-Chem, another regional model, is number 2. GeoChem comes in at number 3. The high split trajectory model from NOAA comes in at number 4. And you can look on down the line for your favorite model. But I'll just highlight as well the AirMod model, which is a local model that was really developed for regulatory applications, which there have been publications on for sure, but it is not one of the more published models. So a little game here, and if we were in person, we could have a show of hands, but you can play this at home. Web of Science citations are one way to think about who's using these models. But the truth is, there's a lot of organizations that want to use models for applications that are not published in Web of Science. And so I started playing around with Google Trends as one way to think about who is using these models. So here are 5 bars representing 5 models: AirMod, CMAC, GeoChem, High Split, and WRF-Chem. You can take a minute to guess which one might be the red and the blue, and which one might be the green and the purple. And then I will display the results, which is basically that we find that at least when I was searching at this for the year from September 2022 to 2023, GeoChem and WRF-Chem were the least Googled, and the most Googled were AirMod and High Split. And I think that this is interesting, not because it changes the value of these different models, but just to recognize that there's a lot of people using models that are not fully reflected in the scientific community. And one of the cool things about Google Trends is that you can look at when are people Googling these data. And actually, when you see High Split, even if you look at a 5-year record, there is one big peak right in the spring of 2023. And again, a little game that you can play at home. Why is there that peak? But I will tell you what the answer is. It has two things that happened in spring of 2023. First, there was a big explosion of a train car in Ohio, and there was also a controversy about weather balloons over the United States, tracing back to China. And so I think both of those are attributing this spike in High Split. And if you look at where people are using these models, GeoChem and WRF-Chem are primarily being used in the United States, depending on when you're searching. Also, China pops up as a main user of those. CMAC has more of a global reach on who's using CMAC. AirMod has the most global reach with users around the world, and High Split is sort of in the middle between those. I mentioned that this is what the path looked like if we looked at that year from last fall to the fall before. But actually, I'm trying to be a little more scientifically rigorous. And so just this morning, I did the same analysis from the 1st of 2020 through today. And actually, the more we get away from that huge peak of that huge peak of high split in early 2023, the more actually we see that AirMod is in fact the most searched for model. Now, this may sound surprising to you if you've never heard of AirMod. It is definitely the stepchild of the scientific community. And I do something like this every time I give a talk where I mention these models because I decided to look for ESSEC and to see where your community was publishing. And so if I looked at ESSEC CMAC, for example, I got 452 hits, and ESSEC and GeosChem is 338, et cetera, et cetera. AirMod is 51, but really I think that's probably an overestimate, because here's what Google told me when I did ESSEC and AirMod is that there aren't many great matches for that. So really, even though AirMod is the most searched for model in the world, it is woefully, in my opinion, underrepresented in how academics are using it. And of course, if I think this, why aren't I using it? And I have started using AirMod. And the reason I've started using AirMod is because it is the only model that is used to determine regulatory compliance with the National Ambient Air Quality Standards. It is used to determine compliance with SO2, because there just aren't enough SO2 monitors to detect all of the sources. And just if you want to know what that looks like, we also run CMAC. And so here on the left is a map of SO2 over a unnamed study site for a particular day in 2019. And each grid is 12 by 12 kilometers. And then what AirMod does is it zooms in, and here's what the same day at AirMod looks like, and where the radius of this search is 15 kilometers. So I could talk more about this, but I don't want to say that advanced models have I don't want to give them the short change. They are super powerful. They're the gold standard. They're the only option if you want to look at secondary pollutants like ozone and really time varying processes. And they're fantastic for decision making. I think it's more just to recognize that there is a broad scope of models that can be used for decision makers. So some lessons learned is that, to me, the best model is not always the most scientifically advanced model. It depends on the application, and that there's a cycle where outreach and research can feed back on each other in ways that I think move forward the research enterprise in an exciting way. Dialogue and relationships can lead to both non-federal funding as well as federal funding, but you really have to work with a partner to find solutions that work for both of you. And I think this is really a negotiation process. And if you don't like the idea of negotiation, I love this podcast from Slate, which is called the Slate Negotiation Academy. And it's just 10 episodes, 10 minutes each, but I think it really hits on a lot of the big picture ideas of how you arrive at a consensus with a partner about anything. And with that, I'll end and happy to take questions.
Hey, thank you so much, Tracey. That was awesome. And thanks for incorporating ESSEC into the presentation. That was really interesting. So if anybody has any questions, now is the time. You can raise your hand or unmute yourself, or if you don't have a microphone, just put your question in the chat. I'll read it out loud.
So I'm happy to ask a question if
Go for
nobody
it.
else does. So wonderful work, Tracey.
Thank you.
Okay, glad you can hear me. One of the interesting questions we always have are, policy makers want to decide, should they spend any money on VOCs or not? And I think we're getting more sophisticated about that. I guess I'd like to get your take on what worries me is people used to say, don't control NOx because it'll make ozone worse. And that's a wrong-headed approach. There are times and places where you want to control both. You never want to let NOx go up. In fact, you never want to let VOCs go up either, because they make particles. So would you refer to those maps you're making as places where it may be on certain days appropriate to go after specific VOCs? And we know from some of the work in New York which ones they might be. So is that how you would phrase the advice to people who are trying to regulate reactive hydrocarbons from paint shops and polyethylene factories and so on?
Yeah, so I think, VOCs are an exciting topic. They're exciting scientifically because, characterizing their sources, characterizing the chemistry, characterizing secondary organic aerosol formation, but they're also exciting from a decision-making perspective, not just on an ozone control and a PM control, but also from an air toxics perspective, and really an environmental justice perspective associated with the air toxics perspective. Because more and more, as we have higher resolution models and higher resolution satellites and a boom in low cost monitoring, there's a much, this is really like a tidal wave of interest in air quality for environmental justice concerns. And what are people breathing who live near these facilities? And when it comes to air toxics, there's just not a robust network of regulatory monitors, in part because these monitors were put in place for ozone photochemistry analysis. So I think that this idea of like, who cares about VOCs and when should we care about VOCs? I think the ozone chemistry is definitely part of the story. And I think I'm so excited about this thread of looking at what does ozone control need on the highest ozone days. And the idea that, in some places, you're becoming NOx limited when you have a lot of trees, and on these warm days, an upsurge in natural VOCs. But I think in other places, and potentially these desert environments like Las Vegas, actually those may be days when you become more VOC limited and need to and the benefit of reducing your anthropogenic VOCs is going to be enhanced. But I would say in many of the environmental justice conversations that I've been having over the past year, often the focus is on the VOCs. And so I think whether it's, there was ProPublica came out with a map showing like, cancer-causing pollution across the United States, which was really an interpolated VOC map, or monitoring networks being placed to support air toxics analysis in LA, California, or the United States. I think that, or even, university-based initiatives to go measure fence line VOCs for communities who are concerned for a specific area. I think that the scientific interest in the VOCs and the policy interest in the VOCs is merging. And I think certainly like ozone control is part of that, but I would say that actually the environmental justice angle may be even more salient.
Yeah, I couldn't agree more. Trouble is, a lot of those toxics are impossible to measure with low-cost sensors, at least with current technology.
Yeah.
So it's going to cost money. Yeah, anyway, Shinrong has a nice toy he'll tell you about sometime. I should let somebody else ask questions.
Yeah, if anybody has any other questions, you can go ahead and raise your hand or unmute yourself, put it in the chat.
Yeah, I had a quick question.
Go ahead.
So I was curious in terms of the outreach and kind of expanding your Python tooling and whatnot. Have you considered tools like that are more cloud-based, like I like MyBinder and doing any sort of cloud computing kind of expansion?
Yeah, so I mean, I guess one thing is that so I am not a software education expert. And I think if I were, I would have lots of innovative ideas. Like I don't even know what those things you mentioned are. But instead, what I hear, like I hear people asking for things, and I think, what is the easiest way to deliver what they're asking for? And at least, when I think about the challenge of on-ramping new researchers into the kind of work we do, which is very complicated because there's so many data sources and there's a lot of different concepts. And I work with a lot of undergrads, really starting sometimes from their freshman or sophomore years. And so historically, actually, in my group for a long time, we used the NCAR command language. And I loved the NCAR command language because it was developed by NCAR, the National Center for Atmospheric Research. And so all of their tutorials, all of their examples, all related to geophysical data. And so lots of NetCDF. So even somebody who had never programmed in any language could follow along with those NCL tutorials and get up to speed. So over time, I trained about 50 undergrads in how to use NCL. But then NCL was discontinued and they moved to Python. But NCAR didn't have the kind of Python tutorials that would allow a novice user to go from 0 to 30 miles an hour using Python. And so I had graduate students who were super smart and motivated, even though they were funded on other projects, and that they were excited about this challenge of how do we support new undergrads in building the data analysis tools they need in kind of the easiest possible way. And so they decided that the Jupyter notebooks, it was something that was used in a few of the AOS classes here at the University of Wisconsin, super user-friendly. They decided to start developing the Jupyter notebooks, and it seems to have taken off. So I'm sure that there are probably systematic ways to be taking that to the next level. But I think one of the things that I think is nice is to figure out how can you do things without making them their own project on themselves, because it's hard to find funding for every new project. But if you can say, well, I'm doing this and I have these students and they're interested in this, and finding a way to make it kind of a side benefit, but it's sometimes a side benefit that may actually have more of an impact than the original work itself.
Yeah, totally agreed. Yeah, my binder kind of takes notebooks to the next level where like any user can open it in an environment and run the notebook without having to, build their own environment.
Oh, cool.
So there's like cloud tools like that and so Jupyter Hub is a way of using Jupyter notebooks, but it's in the cloud and has an environment set up already. So they're just new ways, I think, of maybe broadening how you can access and actually making it even a little easier for groups. We've thought a lot about that in some of the work we've done. You guys, great presentation, and I love how much you've kind of broadened your access and allowed other groups to participate. It's really cool.
Thank you. And thanks for the ideas. That's great. I'll look into those.
Do you have any other questions before we want to wrap up?
So
Well, Van,
can I ask a question?
Go ahead.
Thanks, Dr. Holloway. I had a question with VOCs and measurements of VOC with satellite. Well, one of the very basic things about VOCs are their very short lifetime. They're super reactive, and that causes a lot of attention when people want to use them in their modeling system. I had the issue of we were trying to publish a paper with using VOCs with a statistical analysis, and the reviewers they were saying uncertainty of a statistical model is high. VOC reactions are high. We cannot trust your methodology. So I was curious, with the same, let's say, reasoning, satellite retrievals, the way they're gonna probably do the measurements probably have some uncertainties. and I was curious how you're gonna, I don't know, deal with all of that uncertainty, atmospheric chemistry, plus measurements, retrievals, algorithms. Yeah, I was curious to have your note, and wanted to thank you for sharing the podcast. That was excellent.
Oh,
Sharing
good.
the book and sharing the podcast. I really appreciate these two
Oh, good.
materials, items. Yeah.
Oh, good. Well, thanks so much, and thanks for the question. So, I think with the formaldehyde data from the Tropomi satellite, that's something where, I'm not developing the retrieval. We're using the retrieval in a manner consistent with recommendations and trying to see how can it be used for different applications. And so, we've used the formaldehyde retrieval in part to evaluate the CMAC model, because right now CMAC is the model used by the EPA for the National Air Toxics Assessment so first I'll say formaldehyde is the only VOC that we can reliably get from satellites, and that's the one that's used most often. It's good in the sense that it's an indicator of secondary VOC formation and reactivity. It's bad in that it's one big pool of primary and secondary sources. One thing we've used it for is model evaluation. And because you can calculate the column from the model and calculate the column from the satellite and use it and to see, do we get similar spatial patterns? Do we get similar quantitative values? And in that way, an average over months or seasons. And we published that work in JGR and found, fairly good agreement between the model and the satellite retrieval, but we also look at different satellite retrievals so that we get some estimate of inner retrieval differences. We've also, inspired by a request from one of our air quality managers who wanted to know how well the satellite data reflected what was happening at the surface. I worked with a former student of mine, Peidong Wang, who's now at MIT, to do a comparison of all available formaldehyde surface measurements with satellite data. And, comparing a ground-based measurement with a column is a little like comparing, apples and pears because they're measuring different things. But we wanted to see whether the spatial patterns were consistent, whether the trends over time were consistent. And we found some differences that were helpful to see sort of where might monitors be more reflecting local anthropogenic sources, and also some trends to help understand where we should apply these data. So, I'd say a lot of my work is thinking about, is this a valid application, which is different than what is the quantitative uncertainty when doing a statistical model. And I think that, both are super valuable and they are moving in the same direction. But right now, the applications of satellite data to decision making, I would say, are woefully under explored. And so I think thinking about, how can we be moving the needle to make it more relevant? And then once we see that there's a potential fit, how can we refine it based on better data? And I think it'll be exciting to see how the tempo formaldehyde data changes the game now that it's coming on an hourly basis.
Thank you. Do we have any other questions before we wrap up? Okay, well, thank you everybody for coming. Thank you so much to Tracey for giving us this great talk. This was wonderful. And we will be here same time, same place next week as we continue our seminar series. Everybody have a wonderful afternoon.
Okay, thank you. Bye.
Thank you.